Good afternoon. I am Mr. Ish. Thank you for joining me for this video here. Ink drop in water. That titles this video. You know what we're referring to here. You drop a little volume of ink in water and you know what happens. That ink spot or drop slowly spreads and then the water colors and assumes the color of that ink. At what rate does that procedure or process occur? Well, we'll be looking at that in this video. We're not going to be using the terms such as diffusion, solution, because we're not talking here about chemistry or physics. We're talking here about rates of change in this video. And an application of rates of change is this very concept of ink drop in water. We'll be making several assumptions over here and I'll have them listed over here for you on the side. And we'll make some other assumptions which I have not listed. For this whole video, we're not assuming there's any factor being played in terms of the temperature of the water or the viscosity of that ink. Other ambient factors such as pressure of the system, which could very well affect this whole procedure. Also, there's going to be nothing involved with stirring or vibration, none of that. None of those factors, physical factors or chemical factors that would increase the spread by which this drop changes the color of that water. Everything over here is going to be a natural course as is written here in this problem. And everything over here is hypothetical, but the procedure over here is very much real. So what exactly is this question we'll look at in this video? Well, we have a 1 milligram drop of this blue ink, which is dropped in 250 millimeters cube of water. If the radius of ink drop increases at a rate of 0.55 millimeters per second, how long does it take for that bowl of water to turn blue? What do we have highlighted here? We're starting with 1 milligram of this drop of blue ink. We have 250 millimeters cube of water and assume it's a shape of a bowl. We don't necessarily are talking about a cup of water. We can be talking here about a bowl of water. And if the radius of the ink drop increases here at a rate of 0.5 millimeters per second. So as you drop this drop of ink in water, it slowly expands, and the rate at which it expands, the radius of that is 0.5 millimeters per second. So how long will it take for this bowl of water to turn blue? What are some of the factors we must know from the very beginning? We need to know that the density of water is always 1, meaning 1 milligram per millimeter cube. You have 1 milligram in terms of matter of water molecules per 1 millimeter cube of that solution. We also have a density of ink listed here as 1.25, same units, 1.25, and we assume that 1 millimeter cube is synonymous to an ml, a milliliter. Another thing we're assuming here is that the drop is in the shape of a sphere. We're not looking at a drop which looks something like this. Our drop assumes the shape of a sphere. And you know we're talking here in all regards to three-dimensional objects, three-dimensional shapes. So we're talking about a drop in the form of a sphere. So how do we go about proceeding with this? If you're going to have a little container here with water in it and you were to put a drop, you know from all sides, three-dimensional sides, from all surfaces of this, the ink is going to expand and it'll slowly spread and fill up the entire container, and that the container of water will turn the color blue because we're here talking about blue ink. But before any of that, we need to know how much volume of this ink exactly being dropped into a container of water. Well, we're here talking about 1 milligram of blue ink, but that is not volume, that's mass. If you know that density is always equal to mass over volume, that's a formula which everyone usually knows who has done some level of chemistry or physics, and even in mathematics you'll see this density is equal to mass over volume. We have 1 milligram drop of this blue ink. So we're talking about 1 milligram, and here I've mentioned that the density is equal to 1.25, which we have written over there on the side, 1.25 milligrams per millimeter cube. We have 1 divided by the volume is equal to the density of this ink. We have to calculate for this volume because it'll give us an idea of how much blue ink was dropped into that 250 millimeters cube, or let's just say milliliters of water. So volume is equal to mass over density, which in this instance is 1 divided by 1.25. You have milligrams here, you have milligrams over millimeters cube here in the denominator. When you do 1 divided by 1.25, you'll get 0.8 millimeters cube, and that's the volume of that drop of blue ink. And that's a very crucial piece of information we must know, and I'm taking this and I'm putting it right over here with a V0. We'll talk about this V0 later on, but we're looking here at 0.8. We can say millimeters, milliliters, or millimeters cube. Either or is fine. So we have this very important piece of information set aside. Now what do we need to do? We know that the drop of ink is in the shape of a sphere, it's good to know what's the radius that we're dealing with in that drop of ink. That 1 milligram drop of blue ink, what was the initial radius? How about this? Volume is equal to 4 over 3 pi r cubed. We know that the volume now of this initial drop of blue ink is 0.8. Let's forget the units for this specific computation. 0.8 is equal to 4 over 3 pi r cube, and let's solve for this radius. R cube is equal to 0.8 times 3 over 4 pi, and radius is equal to 0.8 times 3 divided by 4 pi, and it's cube root of all of this, and we'll post that value, and the radius here will be in the millimeter units. And the radius we get for this 1 milligram drop or 0.8 milliliter drop in a sphere format, in a sphere shape, is 0.5758 millimeters. So this sphere of blue ink, it has a radius right here, this radius of 0.5758 millimeters. So now we have another crucial piece of information. We'll put that right over here. The radius, the initial radius is 0.5758 millimeters. All of this will play out in a very logical way, and you will see it take shape and form. So what do we need to know? What are we looking for? How long does it take for the bowl of water to turn blue? We're talking here about time, but we're also talking about a formula, and then therefore we must be looking at some sort of rate of change. How will this rate of change come into play? It would be very beneficial for us to know what the change in volume is over time, because as you drop that ink into water and that ink begins to spread and assume the shape of the container it's in and color that water blue, we know that the volume of that drop expands with time and the radius expands with time. It increases with time. How about this? Volume is equal to 4 over 3 pi r cubed, and we should be looking at the rate of change of the variables that are involved, the volume and the radius. And how about this? The change in volume divided by change in time for the volume variable is equal to 4 over 3 pi, which are constant. You can push them out, multiplied by the change in the rate of the radius r cubed. This, in terms of its derivative, this is v to the power of 1. When you send it through the power rule, you'll end up getting just a 1, because you'll have 1 v to the power of 0, which is just a 1. This r cubed becomes 3r squared. So now all of a sudden we have dv or dt is equal to 4 over 3 pi. This became a 3r squared. The derivative of r cubed is 3r squared. I'll just bring that 3r squared right over here, and then I'll still write the dr over dt, the rate and change of the radius over time. This equation, the initial equation for a sphere, has been modified now to express the relevant rates of change. What do we need to find out, and what do we know? We need to find out this, the change in the volume or change in time, because that factor right there will help us answer our question. It will also help us answer two accessory questions which I'll post right after doing this. Now that we have this rate of change equation in a good format, we can actually plug in what we know and solve for dv or dt. And you can see very easily the 3's cancel out. One is in the numerator, one is in the denominator. They cancel out. So dv or dt, which is what we're solving for, is equal to 4 pi. The 3's canceling out. What's our radius squared? We know this right here is our radius, 0.5758. Assume we're not looking at the units just yet. Square, and the rate of change of the radius, we already know that, 0.55 right here. We solve over here for dv or dt, change in volume or change in time. You need to bring your calculator for this specific part right here. We'll do 4 times pi times 0.5758 square times 0.55, and we get a change in the volume here to be 2.29147. And how can we express that? How about this? Millimeters cube, or you can say milliliters per second, because here we're looking at time in terms of second. That's our rate of change in the volume. Alright, so we've determined this right here, a very crucial piece of information which will help us actually answer our question. How long does it take for the bowl of water to turn blue? Well, we know the rate of change of the radius. We now know the rate of change of the volume. That little drop of blue ink in the water is going to expand at this rate. In terms of its volume, the volume of that sphere will expand in that same rate to eventually fill the bowl in terms of the color. And how can we do this? We know that change in volume over change in time is equal to final volume minus initial volume over final time minus initial time. Hence, this right here is coming into play. What's our final volume over here that we're trying to determine? The 250, because that represents when this experiment is completed and the entire water is colored blue. We know in that sense that in terms of the blue ink, the volume it has assumed is 250. And what's the volume that it initially started out with? It's exactly what we have over here, 0.8 ml. This is 250 ml or 250 millimeters cube. This is 0.8 millimeters cube divided by the time we're trying to figure out. The initial time is 0. When we started the experiment, we started the stopwatch, it was 0. The final time is exactly what we're looking for, and all of this is equal to rate of change in terms of the volume, which was 2.291. We'll eliminate some of these other digits, 2.291. Now you just have to solve for TF, and that's easy. 250 minus 0.8 divided by 2.291, and we'll get our value. And we find out that it takes 108.77 seconds for this procedure. You can call it diffusion, though I hesitate to use the word diffusion, but for this procedure to take place such that the blue ink from the single drop, it will expand from 0.8 ml in all directions to fill the 250 millimeter cube volume capacity of that bowl of water, and it will color it in this period of time. Let's look at two accessory questions. And the first accessory question is this: at what time is the volume of ink 100 milliliters or 100 millimeter cube? Starting from that little drop in the 250 millimeter cube bowl of water, at what time does it expand to have a volume of 100? How can you do this? Again, look at the same equation, change in volume over change in time, which is equal to this value I've put right over here, 2.291 millimeter cube over second. I won't put the units, is equal to the final volume minus initial volume over change in time, which is final time minus initial time. We know the final volume is this exactly what we're measuring. That's our final volume because our experiment is requiring us to measure the time needed to reach that. So for the purposes of the experiment, this becomes the final volume. 100 minus the initial volume, which is 0.8, divided by the TF, the time needed, is equal to 2.291. We just cross multiply TF and 2.291 final time, and I can do this difference and divide it by 2.291, and that'll give me my final time, and I can post that value for you right there. It takes 43.3 seconds. It makes sense. If it takes 108.77 seconds to reach the full volume of 250, but we're only measuring up to 100 ml, it should definitely be less than half this, and it indeed is. So that's a good accessory question A. We'll look at one more accessory question, and that'll be it for this video. Okay, question B, accessory question B is, at 90 seconds, time 90 seconds, what volume of water has turned blue? It should not be too hard. Again, you're looking at everything with this basic equation. Change in volume or change in time is equal to your final volume minus initial volume divided by change in time, final time minus initial time. We know the change in volume or change in time is this value right here, 2.291 millimeter cube over second. And we're saying time given to us is 90 seconds. The initial time when you started this experiment must be 0. The final time is 90 seconds. So you can do 90 minus 0 and you can just bring 90 right over here. We can easily plug in the initial volume because we have that right here, 0.8, but we have to calculate the final volume. And what we can do over here is create our equation. VF minus initial volume 0.8 over 90 is equal to 2.291. You just have to multiply 90 by 2.291 and then add 0.8 to it, and it'll give you your final volume. And let's take that measurement. The measurement over here I get in terms of the final volume is 206.99. I'll just write 206.9 millimeter cube or milliliters. Let's just write that. And again, we seem to have a good answer over here. Think about it. If it took 108.77 seconds to turn 250 milliliters of water blue, all of that, when we're looking at just 90 seconds, which is definitely less than 108, we should be filling a value less than 250 because we're not going to reach the entire volume of that bowl of water, but we'll reach a good portion of it, and that good portion is 206.9 ml. So that completes that question number B over there, and you've seen the question we've taken for you from start to finish and how it played out. This was a good rate of change application involving an ink drop thrown into water or dropped into water, and I had some of the information posted for you and some of the assumptions we made and some of the assumptions we did not account for, which I verbally told you at the very beginning. And you can see how everything played here in terms of rate of change involving derivatives. And then of course the last two applications were all rate of change based, and you've seen that before you. And with that, let's end this video. Hopefully you enjoyed this. Thank you for watching. Stay tuned. Have a nice day.